And there have to be ways to characterize that. There are measurement tools to tell you, you can buy different types of spaghetti, right? You can go to the grocery store and you can buy thin spaghetti, you can buy thick spaghetti. Different length, maybe. My model and my analogy of polymers is spaghetti. How many of you have ever boiled spaghetti and didn't finish it, and they kind of like were left in the fridge and they got stuck together, crumbled? Do you know what I'm talking about? Okay. That's what polymers really are if you look at the macroscopic scale. So it's about how long that spaghetti is, it's about how well they stick to each other, and some of those spaghetti can have different structure and be branched. So let's talk about statistics a little bit. So the molecular weight distribution is represented here. This is the amount of polymer versus molecular weight. So you're going to have some distribution. And then there are two parameters that we want to look at. One is the number average, and the other one is weight average. The bar here above M means average, N stands for the number, and W stands for the weight, and here's the formula. Okay, so we sum the total weight of the polymer divided by the total number of the molecules in the polymer, right? Like talking about that spaghetti, you weigh all of the spaghetti, and then you count the numbers of spaghetti, and that's how you get the number average. The weight average is where the W here is the weight fraction of the chain of the size in the range I. So now we're going to do an experiment and look at sample calculation of this. This is, there are 10 students in the class, and this is their weight in pounds. Okay, and varies from 104 to 380 pounds. And the question is what is the weight average of the students in the class? And based on the number of fractions, fraction of the students in each mass range, and based on the weight fraction of students in each mass range. So this is the analogy that we're going to use to apply for this concept. Okay, so first step is we're going to sort and bin the weight into different categories, and we're going to use 40 pounds ranges. Okay, so here you see 81 to 120, 121 to 160. It goes all the way to 400 pounds. And then here we have the number of students that fall into each one of those categories. The total number has to be added to 10, right? And then we can calculate the mean weight mass, right? So this is the average for the 2 students, and this is for 3, this is for 2. There's nobody here, and there's 1 student that's 380 pounds. So if we add all of that together, we get 1,880 pounds. And then we need to calculate the number and the weight fraction of the students in each range. We calculate the x sub I as n sub I over the sum of all the n sub i's, and the w sub I of n sub I times w I, the weight divided by the sum of ni times w I. Right. For example, like in this range from 81 to 120 students, there are 2 students, and divided by the total number of students is 10, so the fraction is 0.2. Let's say between like, in terms of the weight, which is in this range, we have 2 students times 110 divided by the total weight, which is 1881, and that gives us 0.117 fraction. You see, there's a different way of calculating it, and that's why we get a different number. And then we can do it for each one of those ranges, and the number fraction and the weight fraction, and you just saw the difference, that those numbers are going to be different because we're counting it in a different way. And if we follow all of the math, then we're going to see that the number fraction average is going to be 188 pounds, and the weight average is going to be 218 pounds. So there are 2 ways of calculating it. How many of you have taken a statistics class? Okay, was it good? All right. I've taken a statistics class, so there was a lot of ANOVA simulations and things like that. And I'm going to ask you a question. If there's some data and you need to report this data, let's say average grade in this class, whatever it's going to be, or average value for the last exam, right? There's an average value. And then we can report two things in addition to that: standard deviation and standard error. How many of you remember the difference and which one is going to give you the narrower range, if you remember? And if we're talking about standard deviation, what kind of distribution are we assuming? If you recall, we're assuming Gaussian distribution. And what does Gaussian distribution mean? The bell curve. And what's the meaning of the bell curve, if you recall? That it is symmetric. Okay, that is symmetric distribution. So let me ask you this: is this distribution symmetric? No. So the one thing about statistics is you kind of like need to know ahead of time the data that you're dealing with, and whenever you're publishing that data, if you want to have smaller error bars, you report standard error versus standard deviation. Okay? And never mix the two, because that's, you know, a common, I wouldn't say discrepancy, but certain things make sense and certain things don't. I'm looking at the data from this concert from Diana Ross. It was a concert this last Saturday. And I have a feeling that most of the 100+ videos that I posted are going to be over 100 views, so I'm going to get a lot of statistics on that. So it would be interesting. But I think that Diana Ross is going to be evenly distributed as far as the views for you know, the distribution between the gender index. But we'll see. Okay, any questions about the statistical distribution and characterization of polymers in terms of the molecular weight? Number fraction versus weight fraction? Okay, degree of polymerization is another parameter that is the average number of repeat units per chain. Okay, so here is the repeat unit, and we can just count that number. And the degree of polymerization is 6, where small m bar is the average molecular weight of the repeat unit for copolymers that are calculated as the sum of the chain fraction times the molecular weight of the repeat unit I. Right? So we have m sub n, which is the based on the number fraction divided by the weight of the repeat unit. So essentially what it does, it counts how many of those repeat units are in the chain. Make sense? And what did I tell you last time for polyethylene? What does the weight molecular weight control? It's going to control whether you're going to have a candle or whether you're going to have a grocery bag, plastic grocery bag made from polyethylene in Publix. You can visualize and imagine the big difference, right? And who controls the molecular weight? Well, you can argue nature, but who is using nature to control the molecular weight? Is the process engineer, which is, who is that? It's you, to control the process, to control the structure, to control the properties. There are linear polymers. You can see that there's bonding. And by the way, what kind of bonding is between the atoms inside the molecular chain? What kind of bonding do we know? Is it metallic? Is it ionic? Is it covalent? Is it secondary, like van der Waals? Take your pick. Multiple choice. Okay, what is covalent bonding? What happens during covalent bonding? All right, what is bonding? How do atoms become ionized? What does it mean that the atom is ionized? Metal, non-metal, fine. But what happens with metal, non-metal? What do those two atoms, metal and non-metal, do? What do they do? Gives an atom, gives the whole self to the other one. Yeah? Really? Which part? Electrons. Okay, very good. So once there's transfer of electrons, right, that one becomes a positively charged, the other one becomes negatively charged, right? And you remember that experiment that I tried to do where I lifted the piece of paper with whatever I was using? Remember? Charge transfer. What about covalent? They share the electrons. Okay, and that is the strongest type of bonding, if you recall. Okay, so inside the polymer chain, the bonding is covalent, but between the chains, it's secondary bonding, so it's weak. And that, my analogy, my model of the spaghetti that is stale and left over in the fridge that you didn't finish, and they stick together, they're still moist, but you need kind of like separate them from each other. Okay. Those polymers can become branched. And you never had this kind of spaghetti, right? But here you go. And then there's another process called cross-linking, where you can have a short spaghetti that will glue pieces of other spaghetti. Or it can form a network like this. So these are the different types of linear branch, cross-linked, and network for the polymer. Which affects their molecular shape. So molecular shape is also called conformation, is the chain that's binding and twisting that are possible by rotation of carbon atoms around their chain bonds, and not necessarily braid chain bonds that alter the molecular shape. So here you go. You see here's carbon like this, and then all of a sudden, boom, there's a break in the chain and there's a twist. So the molecule, even though chemically it's the same, it has the same amount of carbon and hydrogen, but its three-dimensional arrangement is different. See that? The other parameter that we also are interested in is chain end-to-end distance. And that's when you have your spaghetti and it's tangled, and what is the distance between the ends? Right? So when the spaghetti it hasn't been boiled. It's the length of the spaghetti. But once you boil it, it's going to be tangled, and somewhere there's going to be this distance, which material science is all about finding a length scale, like how big. The size matters. That's what you can think of. So that's what we're looking at here, is the size. And the other one is called a stereoisomerism, is when you have like a mirror image. So here you see a free radical on one side or on the opposite side, like this. You realize that when you look at the mirror image of yourself, your right side, which is your right side, is on the opposite side. So stereoisomerism are mirror images, and you can't superimpose them without breaking the bond. So here's a configuration for the polymer. Another property is called tacticity, which is stereoregularity or spatial arrangement of this free radical unit along the chain. And there are two types, either isotactic or syndiotactic. And iso in Greek means the same. So this radical is on the same side of the chain, as you see here. Syndiotactic is when it's alternating. Boom, boom, back and forth. Bottom, top, bottom, top, bottom, top. Or it can be atactic, meaning that it's randomly distributed. Believe it or not, it's very easy to just, draw you a picture like this. It's a different story to actually try and determine that. We're not determining this directly. There has to be some sort of indirect method to deal with it. And those methods can be very elaborate and very expensive. So it has to be worthwhile to do it for this. All right. Cis versus trans isomerism. A very important one. Here is the natural rubber, or cis isoprene. This is trans isoprene or gutta percha. And the only difference is that here for the cis isoprene, the CH3 group and hydrogen are on the same side, and here it's on the opposite side of the chain. Have you ever heard about rubber vulcanization? And if you know what that is, let me know what it is. Have you ever had a flat tire on a bicycle? What do you do if you have a flat tire on a bicycle? Replace it. Replace it with what? With another tube, right? Which you get where? Store. Or what if you are, on Pinellas Trail and there's no store? Or you know that you're going to be riding your bicycle for a long time. You're going into the woods. What do? You bring a spare, right? But the spare is, when you pack is a big deal. So now they have a kit for you to repair it, which involves a glue, because we do have advanced glues that would actually do the job. But back in the day, you would take a piece of untreated rubber and take a sandpaper and clean out the spot. By the way, how do you find where your tube is leaking? Get it wet, get it in the water. Yeah. But then you need to dry it to make sure that you can cure it. And then you put that piece of untreated resin, and there's a device that applies pressure and heat and get it vulcanized and becomes one piece. So I used to do that when I was a kid because there was no store to buy the extra tube. And if you run out of the tubes and there's no more rubber or anything, you know what you do? You don't know? You take your old t-shirts and you put that instead of the tube. And it can last you for a little bit. I don't recommend it for safety, but that's sometimes what you have to do when you live in a poor country. Okay, copolymers. That's when there are more than one that are polymerized together. And here you can see there's one chain and then there's another chain. In this case, it's as random. So A and B type, the red and the dark ones are sequentially here that are random. They can be alternating, they can be block, and they can be graft. So block is they're alternating here one after the other. Block is when there's a certain molecular weight associated with each one. And then the graft is when the grafts are grafted onto the backbone like this. Believe it or not, polymers can be crystalline. What is the meaning of the word crystalline? Periodic array. Okay, try to boil spaghetti, and once it's done, put it back in the same configuration that they came in the box. Is that going to be an easy job? Not really. It can be done. So, crystallization consists of the two processes. Can you please remind me what those two processes are? Like when water turns into ice, let's say. That's crystallization. Whenever you have a party, you ask your buddy to bring a bag of ice, right? Why? Because your ice cubes didn't turn into ice. They're still half ice, half water, right? And it takes time. And during that time, what happens? Do you remember the science dude that had supercritical water in his fridge? And then I showed you the video, remember? He took that bottle of Fiji water and he banged it, and you could see the propagation of ice through the water, which was a phase transformation of water into solid, which followed two processes. What are they, if you remember? The first one is starts with the letter N, nucleation. And what's the second one? After it's nucleated, was born, what happens to you every year? Nucleation and growth. Okay. So in order for this polymeric chain to attain its structure, it needs a lot of time because it's very cumbersome. And this is an example of polyethylene unit cell. How? Well, imagine you can take this spaghetti and you can just fold it like this. This is the chain folded structure. The height here is only 10 nanometers. So that's about 100 angstroms. And most of the polymers are not 100% crystalline. There are some regions like this, which is shown here schematically, where you have the crystalline region, but in between there is an amorphous region. And then we can calculate the percentage of crystallinity, because many properties would depend on this percent crystallinity. And we can alter that by heat treatment. So if we can heat it up and give it time, it would rearrange into the better periodic array. Can be characterized, so we can look at it in the microscope. These are folded chains of polyethylene. You can see it here. There's a scale bar is 1 micron. And this only happens in a very slowly and carefully controlled growth rate. So a furnace that you need to control the temperature very accurately and keep it there for a very, very long time. Most of the polymers, as I said, are semi-crystalline, so we have this chains that fold into the spherulites, and this is the direction of the spherulite growth from the nucleus, but in between there is some amorphous material, and as a result they can form an interspherulitic boundary, kind of like what happens in metals during crystallization, where we control the grain size, which has a lot of effects on the properties. So this polymers would have spherulite structure, and we have alternating chains that are crystalline with amorphous regions. And because it's very directional, it can happen relatively fast. So it's all about, because it's costing you, any kind of energy input, right? You need to have a furnace, and you need to have the furnace at a certain temperature, so you are providing either electricity, which means that you burn something somewhere. Electricity is considered to be clean energy at the source, but not how it's generated, unless maybe it's hydropower, so many people don't quite realize that. And here's an example of spherulites and polyethylene, and you can see it in polarized light, which is characteristic Maltese cross for each spherulite. And how do you produce polarized light? Through polarizer. Like these glasses are polarized. Do you have any questions about polymers? I can show you some applications. This is a paper we just published in Optics Letters. And the idea is that you can have a shrink fit on a bottle. This is a bottle. And because of the geometry of the bottle, you just need to apply the heat, and so it would shrink onto that. Here is the color. This is the actual color. The idea is to make sure that you can check for authenticity. Like you buy something, is it fake or is it real? And as a result, using this technology, you can produce a barcode here that can be read by a barcode code reader. So I've been working on this quite a bit. It's kind of interesting, and all you really need to do is just have layers of like polyethylene, for example, and as a result of this polyethylene, you can form different color. You see? And this color is passive color, or it can be only visible, let's say, in UV light. Have you traveled lately? I mean, back in the day when there was TSA, what do they have? They have a flashlight, right? And they look at your driver's license. Why? And what is that special flashlight that they have? Or maybe when you go to a club, fancy club, they have that as well. So what is it so special about your driver's license that they shine UV light at your driver's license? It has a special film, and this film has the blue color, right, or the white color. It's the same optical effect when you go to a club and they have this special lighting so your white shirt is going to glow. That's the idea. This is the number of layers versus a parameter that deals with the color difference. You see? And most of those polymers are commodity, which means that they're cheap. Polydimethylsiloxane, PDMS. What's the other common term that's used for this material, if anybody knows? Silicone. Caulk for windows and such. And depending on the ratio of the filler versus the binder, you can have different properties of that. This is why when you go to Home Depot or Lowe's, one tube is $10 and the other tube is $2. But one is rated for some chemical applications, has a warranty of 10 years. It's UV resistant, and the $2 is not. So why does that matter? Because of its mechanical properties are going to be different. To control the process, to control the structure, to control the properties. So here's the amount of cross linker, and this is how the elastic modulus changes. You see it's here from like 0.5 megapascals to 3.5. And you can make it so that it is tacky. When was the last time you got a credit card in the mail? It's glued. The credit card is glued to a piece of paper, right? But it is a special kind of glue that it's only there to secure the credit card for a short period of time. You can just roll that off with your fingers, right? But it's sticky. Who controls that? They have a process so that, there has to be a chemical engineer that figured this out. Maybe my buddy that works for Med, the paper company, that develops, or maybe 3M. You can see here that by adding the different amount of the curing agent to the PDMS base, you can control the mechanical response of your product. And here's an example of how you can show a schematic. It's not a pretty schematic, but I can tell you that this looks prettier than the actual device, and as long as you convey the message like this, it's not 3D. It pretends to be 3D, but it's not. My idea was to use a flat punch. Here's a sample. Here's a pen. And this is an indentation. So you have a surface of a tacky polymer. And tacky means that it sticks if you touch it with your finger. So you bring down the tip from the nano indenter, and when it's close enough to the surface attracts it. You can see this pull in, boom. If it's close enough, it attracts it. And then you continue to push, it pushes, and then you do the pull off, and this is the pull off. So the surface kind of like sticks to the tip, and once you let go, interestingly enough, this transducer starts to oscillate at a resonance frequency. but the polymers are viscoelastic, meaning that if you give it enough time, it's going to recover completely. You can see here that here's the data. 60-second unload, which is here, 120-second unload, which is here, and 400-second unload, which comes back to the 0. So if we look at the maximum displacement, like percent recovery, 99% of it is recovered as a function of this holding time. I'm yet to find a student who would be interested enough to model this and maybe write a master's thesis about it. The data is there. I have tons of data. Just never had the time or the labor hands to analyze it, but this is a method of extracting viscosity, and also there is, for polymers, there are two types of parameters, which is the storage modulus and the loss modulus. And one part is related to the spring, and the other one is related to the dashpot. And since we're on the subject and I can demonstrate, I'm going to do this experiment. So here's the rubber band that I had. Your lip is a very good temperature sensor. So I can feel that this rubber is colder because I can feel the cold. And then I just stretch it, and I can feel the heat. Now, once it's stretched, I let go, and I release, and I feel the cold. And you can do it with your own rubber piece to accommodate for this. Now, this is a famous experiment in material science. When you go like this, and as you feel it's warm, then you let it equilibrate with the temperature like this, and you let go, and you feel the cold. Because your upper lip is a very, if you're shaved, is a good temperature sensor. So by doing this, you can feel the temperature differential. And I'm not sure exactly how much it is, but at least I would say maybe 1 degree. So what does that mean? It means that when you're testing the mechanical properties of polymers, it's not a simple tensile test, like that tensile machine I brought to the other class. It matters how fast you do it. So you're going to get different response if you do it fast versus if you do it slow. And what you see here is the storage modulus as a function of the frequency in hertz. So from 0 to 300 hertz. And this is the loss modulus that deals with the pot part at 100 hertz. And the reason I outline here 100 hertz is because we've done this in terms of the oscillation. So the way you bring this tip down, it's in contact, this cylindrical punch, and you start to oscillate it. Believe it or not, I had this student from Italy who was a USF, into USF student. We used to have this program. And one of the problems that we ran into doing those experiments is that when you have a flat punch and you come with the surface of the polymer, you do not have a complete contact. This is the main reason why, for indentation, people are using some sort of a pyramid to avoid this effect. But for pyramid, you don't know what the contact area is. So the idea of using a flat punch is that the contact area doesn't change. All right, so what we did, these are the low displacement curves. So we have this flat punch, a cylinder, right? And the sample surface is not parallel. So the idea is to bring that sample into contact with the tip and keep pushing, keep pushing, keep pushing, keep pushing, keep pushing until the full contact is developed. Look at these curves. We start with less stiff and go up in stiffness. 50 micron displacement. And then we reach the saturation. So once the saturation is reached, that's how we determined that it was full contact. And you can see we went to 50 microns, then to 52, then back down to 50, and the stiffness didn't change. And believe it or not, he was able to write master's thesis just out of this simple experiment, which we published in Methods X journal, which used to be free. Now you have to pay like a couple $1,000s to even publish a paper there for their article processing charge. Any questions? So once we have an idea of the structure of the polymers, right? What was it called? Like the basic things. Polymer structure, right? To control the structure, to control the process, to control the structure, to control the properties, we can look at the characteristics, applications, and processing. And how they're tested in terms of their properties, how those properties are affected by microstructure, if there's any way to make them better, maybe they can be anisotropic, if we can do some sort of annealing, and how the temperatures affect their properties compared to polymers and ceramics. I'm sorry, to metals and ceramics, and how they can be processed. By the way, so that we're on the same page, where all those plastics come from? When we talked about metals, we talked about refractories, right? So there's iron oxide that comes from Australia. There's red ore, goes to China, and in China they make metal out of that. They make kind of steel. Okay? What is the source material for all of the polymers? China? Ukraine? Anybody can make some sort of a connection? Let's have a discussion. Where those polymers come from? What's the starting material for all of the polymers? Polymers are hydrocarbons, so they contain hydrogen and carbon. Okay? Crude oil. Okay, very good. So everything comes from oil. Do you see, the oil is not just gas that we buy at the pump, at whatever it is, $4 a gallon now. It's everything else that's made from that crude oil, including the plastics, including your plastic bags in the grocery store, including, look around, a lot of polymer products. But okay, let's go back to this properties. This is stress versus strain. And even though those are polymers, they can be brittle polymers, right? They can behave like glass. They can be plastic. So it's not exactly like metal, but the characteristic of the stress strain curve is like a metal because it yields. Or it can be an elastomer, like this, nonlinear elastic solid. And obviously you can see here the slope, which is the elastic modulus, is much less than for metals or ceramic materials. They're much less stiff. And the fracture strength is only about 10% of the metals. But they can be deformed more than 1,000%. For most of the metals, it can be only deformed to 10%. So this is 100 times more. And again, why does it matter and how it applies? All three classes of materials are represented in a beverage container. plastic bottle, aluminum can, and a glass. And you can imagine what happens once you drop it on the floor. So the polymer is the one that can sustain very large deformations. So let's look at what happens when we are extending the polymer and why they behave the way they behave. For the brittle polymer, you can see that initially those chains are aligned along the tensile direction. Let's say for a cross-linked polymer. And then those bonds get stretched, but they don't get realigned that much. And they fail. For a network polymer, this is initial configuration and this is the near failure. And cross-linked means that there's the cross-linkage between the chains here. Let's see what happens to the polymer that kind of like resembles metal behavior. For semi-crystalline plastics, here it is in the undeformed state. Then amorphous regions elongate, and then there's onset of necking. Then we have alignment of the crystalline regions, followed by the crystalline blocks segregation, and finally fibrillous structure. So all of that stuff gets stretched along the tensile direction. This is often accompanied by the change of the color. So you could have a film that's transparent and you start to stretch it with your hands and it becomes white. This is going to be important when we talk about optical properties. So what can we do to improve? We can do a drawing, which is how a fish line is made, by taking a monofilament and stretching the polymer prior to its use, by aligning the chains along the stretching directions. It's one direction. As a result, there's an increase in the elastic modulus along the stretching direction and also increase in the tensile strength along the stretching directions, but decrease in ductility or percent elongation. So all similar to metals, all of this processing kind of affects this. You make the material tougher, stiffer, but at the same time, you reduce its ductility. Also, as a result of that, we can do the annealing, which would decrease the chain alignment and can reverse some of that by reducing the modulus and the tensile strength and enhancing the percent elongation. And it's kind of like contrast to the effects of cold working in metals. Let's look at the rubbers or elastomers, which is the green curve over here. So elastomers are characterized of nonlinear elastic deformation. Nonlinear means that it's not a straight line, it's rather a curve, but it is completely reversible, meaning that you go back to zero strain. So initially we have amorphous chains that are kinked and cross-linked. Over here, this still elastic reversible deformation, and finally it is still cross-linked, but the chains are straighter. So this is opposite to the brittle behavior and the plastic behavior that we discovered. And there's a entropy term to this, which is why the rubbers change their temperature when they're stretched or when they are when the load is released. all polymers fall into one of the two categories: thermoplastics and thermosets. Let's discuss. For thermoplastics, there's less cross-linking. They're typically ductile. They're softer when they're heated up. And examples of polyethylene, polypropylene, polycarbonate, and polystyrene. The thermosets are heavily cross-linked, like 50% of the repeat units. They are hard and they're brittle, and they do not soften with heating. Examples are epoxy and polyester and phenolic resins, and vulcanized rubber. So what we can do is we can look at the temperature versus molecular weight, where here it is liquid, then it turns into the viscous liquid, which can continue to be viscous past the melting temperature and past the glass transition temperature. And here's the rubbery region, tough plastics and partially crystalline solids. So depending on the combination of the temperature and the molecular weight, we get totally different response. Thermoplastics can be recycled, thermosets cannot. And we're going to talk about recycling. I mean, you can always burn, you can always shred, but recycling means that the material goes into the same product it used to be. Like you recycle a plastic bottle, you make a plastic bottle out of the recycled plastic bottle. This is complete cycle of recycling. As I said, there's a very strong dependence on the temperature and the strain rate. So here you see the stress strain curve for PMMA, polymethyl methacrylate, or plexiglass at 40 degrees centigrade, 20 degrees centigrade, 40 degrees centigrade, and 60. You can see that the strain can go up to 1.3 actually. So you can stretch it for a very, very, very long strain. But increasing the strain rate has the same effect as decreasing temperature. So if you do it slowly, you get a lot of deformation. If you do it fast, it's probably going to rip, which I don't want to do. Or maybe I do want to do. Let me see. That hurt. Well, that means I can do it again. That hurt too. Don't try it at home. But, well, if I do it slow, I cannot even do it. I can't. I'm not, well, there you go. That didn't hurt as much because it broke somewhere in the middle. So here you have a demonstration of the strain rate dependence of the rubber. Okay. The glass transition temperature. We discussed the glass transition temperature when we talked about ceramics. Let me tell you about an experience I had. See, life is, a lot of it is about your experiences. And I was lucky enough to work on some cool projects. So here you see a liquid, right? If we slowly cool it down, then the volume drops down, and that's a semi-crystalline solid. If we allow enough time, then it drops down further, and then it can turn into the crystalline solid. But if we are cooling it down faster, then there's no discontinuity, there's a change in the slope, like this. Did I tell you I worked at Motorola before becoming a faculty? Okay. Back in the day, Motorola used to make some interesting products, like processors for Apple computers. I don't know if you know that. And then at some point, Apple switched to Intel processors, and there are different product lines. The first product, commercial product Motorola made was a battery eliminator, which was basically like a power supply that nowadays you use to charge your cell phone. The reason that the company's called Motorola is because it's owned by Galvin family out of Chicago. They put a radio in the car. That's why it's called Motorola. Who would have thought that you want a radio in the car, right? Well, you still have one. The other part of the technology back in the day is called Smart MOS technology. And those are the chips that are made for automotive. And the biggest two consumers, the people that were buying chips from Motorola, are Ford and Mercedes. And they were making those chips that maybe control the seat, or there's quite a bit of electronics in the car, but back in the day there was some, but not that much. Anyway, if you buy a laptop, or if you buy a computer, or if you buy a cell phone, the processor can be expensive, like in the hundreds of dollars, and the consumer would pay that price. If you're talking about car, the electronics has to be inexpensive. I mean, unless you're dealing with Tesla, which is a different story. Part of the price and the cost of the product is packaging. And for a semiconductor chips, it's a big price. The direct competitor of Motorola at the time was Infineon. And the package can be ceramic or it can be plastic. And believe it or not, the chip has to pass a very rigorous test, a temperature test, of minus 50 degrees to plus 150 degrees. Why? Because the same car, whatever the brand, is going to be used in Alaska, in Minnesota, and it's going to be used in Texas and Florida and Arizona. So that's why there's such a large spec. So all of a sudden, the product that Motorola sells is failing high temperature test. Meaning, here's a chip with all the leads. The leads are connected to the circuit, and this chip is placed on a hot plate. And this plate is raising the temperature to 150 degrees, and all of a sudden at 130 degrees the device stops working electrically. And obviously everybody's not happy. And not just not happy, upset. Because that means that Ford and Mercedes cannot buy the Motorola chips and package them into a circuit and sell it as part of their product. Motorola is in the semiconductor manufacturing business, at least was at the time. Then they spin it off and that became Freescale Semiconductor. They were losing $4 billion a year, that part of the business. The supplier of the plastic, which I guess I'm allowed after so many years, it was Dow Chemical, changed the formulation of the plastic. They dropped the glass transition temperature by 20 degrees. So instead of having it at past 150, it started to do the transition at 130. And this package physically bent the silicon chip. so that it stopped performing electrically. How did we deal with it? Well, first, we took the chip out of the package. I had like 5 technicians reporting to me. So they carefully ground that plastic to take the chip out and still have the electrical connection, and heating it up, and all of a sudden it's passing inspection. There is technology called strained silicon. If you physically bend silicon, you can change the band gap of the semiconductor, which I believe we'll have the time to discuss in this course. That's why AMD processors get about 20% performance increase in terms of the frequency for the same product. Okay, so what happens here is the change in the volume here during the glass transition, and that change in the volume physically bend the chip. So here you can see that increasing melting temperature and increasing the glass transition temperature increases with the change stiffness. The change stiffness is increased by the bulky side groups, and you can have, if you cool it fast, you can have polymer in the glassy state or semi-crystalline state or the crystalline solid state. And every time you're going to have better packing. Time-dependent deformation. Here's a tensile test where we apply and we hold it under load, and we do what's called stress relaxation test. So we hold the strain constant, and the stress just continues to drop down as a function of time. So we get a plot of sigma over t. And then if we look at this parameter versus temperature, then we have the rigid solid, transition region, and the viscous liquid region once it's completely in the liquid state. So up to 190 degrees centigrade, where the glass transition temperature is maybe about 80 degrees centigrade. So one of the main important parameters for any kind of plastic is the glass transition temperature. There are ways to deal with that. Next semester, I'm scheduled to teach fracture mechanics, which deals with the resistance of crack propagation. Here's an example of crazing, which is plastic deformation of spherulites in the crack wake, and formation of microvoids, which happen ahead of the crack tip, but this is the mechanism for the propagation of the crack, and this is actually a toughening mechanism. That's why polymers are typically tough, and they withstand crack propagation very well because of this mechanism. Making polymers, making plastics. There are 2 types. There's a polymerization, or addition of the chain nourished to the existing chain, like this, Or another one is condensation. So chain polymerization or step polymerization. We start with a free radical, then we add the mer, and then we can propagate this chain, making the spaghetti longer, until it is terminated. How is it terminated? Well, by another free radical. Who controls that? A process engineer, which is you. For the condensation or step polymerization, here's the hexamethylene diamine, which has the hydrogen on one side and the OH group on the other side of adipic acid. And that's how you form nylon 66 and some water. So there's a chemical reaction that happens to form nylon. What else can we do? Well, we can put different kinds of additives, fillers and plasticizers. The fillers are typically materials that are cheaper, kind of like to fill them up, that's why they're called fillers, decrease the cost, like carbon black, or silica gel, or wood flour, or glass, or limestone, or talc, whatever you can put in there, right, to beef it up. Or you can add a plasticizer, which is reducing the glass transition. It can change the glass transition below the room temperature, and that's how you can make it soft for processing. Like PVC, because PVC is intrinsically brittle. The problem with the plasticizer in the polymer network is that it's practically impossible to get rid of it, which eventually this residual plasticizer causes environmental degradation of the polymer with time. And I know it is not cool in Florida or anywhere, but if you have a used car, how many of you put something on your dashboard, like a carpet or some sort of a thing to protect it? Anybody? Nobody? How often do you clean the dashboard of your car? Because it accumulates dust, and if you don't do it every month or every couple of months, it becomes filthy. You know what I'm talking about? What do? You clean it? Your dashboard is exposed to UV light. Your car is parked here, right? It's being blasted. And then eventually, the car is old, that dashboard becomes sticky and cracks. There's one way to prevent it, is to put a custom piece of carpet to protect it from UV exposure. And I know it is not cool, everybody tells me it's not cool, but if you look at the dashboard of my car, underneath the carpet piece, it's like brand new. So for whatever that is worth. All right, I'll see you next week.